Welcome to the Siemens EDA podcast series on 3D IC design, brought to you by the Siemens Thought Leadership Team. I'm your host, John McMillan. In our last podcast on 3D IC architecture workflows, we talked about how system or microarchitects determine how to partition a device's functionality. Today, we will discuss what a 3D IC physical design workflow looks like, from prototyping and planning through system technology, co-optimization, and through to substrate routing and verification. I'm pleased to introduce my special guest, Mike Walsh, who is the Technical Applications Engineering Director of the Technical Solutions Sales team here at Siemens Digital EDA. Welcome, Mike, and thank you for taking the time to talk with me today about what a 3D IC physical design workflow might look like. And before we dive into the discussion, would you mind giving our listeners a brief description of your current role and background?
Hi, John. Thanks for inviting me onto the podcast. My name is Mike Walsh, and I manage Siemens EDA's worldwide team of IC packaging product specialists. We have a team of roughly a dozen specialists spread across the globe supporting our leading edge customers. I've been with Siemens EDA or Mentor Graphics since 1992 and have been focused on the IC packaging domain for the past 10 years or so, working with leading edge customers on their complex IC packaging design and verification problems.
Thanks, Mike. Given there has been a great deal of growth and development in the area of advanced heterogeneous packaging in the past several years, after the architecture has been defined, what are the typical design flow steps recommended or used for these multi-die and chiplet heterogeneously integrated assemblies?
For the purposes of this discussion, I will use the term substrate to represent the range of interconnect solutions which fall under the IC packaging domain. Here at Siemens, we recognize the challenge of designing an organic substrate are very different than designing a silicon interposer. At a macro level, there is quite a bit of similarity. How do I define and implement the desired connectivity regardless of the interconnect technology that's being used? So we tend to engage with customers at one of 2 points in their substrate design process. Either very early when the design process is first being planned out, connectivity is being defined, or we engage late in the design cycle when the customers are worried about how to verify their complex 2.5D or 3D IC system that they're building. We kind of approach this from 2 different directions, and we'll talk about both. The days of managing a single die package with an Excel spreadsheet are long gone, and that was the methodology used by many customers for many, many years. But with the explosion of AI or high-performance compute silicon interposer designs with 2, 4, sometimes even as many as 8 high bandwidth memories or HBMs, the emergence of fan-out wafer-level packaging, embedded bridge technology, and the growth of system-in-package type designs, which have hundreds, sometimes even thousands of components, the connectivity problem is becoming a focal point for many customers and one that they're really worried about. With those customers, we engage early and help them put together a solution to manage this interconnect challenge that has really become a problem of complexity that's just not well suited toward a spreadsheet. One of the problems we see in particular with interposer design with its relation to silicon or chip design and is compounded by the emergence of chiplet solutions, and we see this just growing, is the various disparate data sources. So a company that's using chiplets and designing their own silicon to work with them may have inputs in multiple formats, such as GDS for their chiplet provider. They may be working with Verilog and the LeftDef for their own silicon. They may be working with CSV for the ball out or the C4 bump plan for their interposer. And how do they bring all of these various pieces of data together and make sense out of it into something that they can use to manage their connectivity? So this challenge of not having to re-implement, redesign, recapture the design elements from their native format and use them as they are becomes a real critical part of the design process, especially those who are worried about this early in the design process and not late in the verification stage. So a substrate design team needs a solution which can deal with multiple data formats quickly and accurately without having to translate the data into something else and bring it into a single cohesive system representation in Netlist. So for an example, multi-die systems, often there will be a verification team that's working with the silicon team to verify the various interfaces between memory or standard interfaces like USB or PCIe, things like that. So this verification team has got a Verilog representation of the design that's been verified with a comprehensive test bench for all the various interfaces. It's working with the actual RTL from the silicon team. It's well understood and known good. There's no reason to recapture that netlist to put a system together for the implementation of an interposer or package. The design teams want to just import that and use it as is. So having a solution or a platform that can deal with that sort of input, where you get the standard parts like memory from those vendors and the chip design from the chip team, and then the netlist from the verification team that brings it all together, and be able to import those pieces and use them as is really critical. And that's what Siemens is working on with many of our customers. Given when we have the opportunity, we encourage our customers thinking about how they're going to verify their design and plan for that from the beginning and not worry about it until the end. When a verification of the independent pieces is left to the very end of the design cycle, often design teams are working with fixed data that they have to make adapt to figure out whether it connects correctly. And while we can do that, it does often find issues very late in the design cycle. So whenever possible, we try to encourage the customers to think and design their system with verification in mind at the end, and using a planning tool to manage all of these data can make the design team's life significantly easier. And we often will refer to this as kind of the golden net list. It's no longer kept in a spreadsheet somewhere, but kept in a planning tool that replaces the spreadsheet. The Siemens connectivity management solution is a cockpit of sorts, and by bringing all these pieces together, it enables early analysis and collaboration, or often referred to as TCO, with a co-optimization by doing early analysis and trade-offs for various reasons. Doing this from a planning tool and the integrations that tool offers makes it easy for design teams to make intelligent decisions early in the design cycle. And as the design matures and the questions about correctness can be answered as part of the design cycle and not waiting until the end. So that's kind of how we see the design flows maturing with the modern 3D IC type designs that we're working with customers on at these days, John.
Well, that's a pretty comprehensive design flow you described there. Can you give the audience an overview of each step and the relevant important points of each?
Sure. I can do my best to highlight some key areas. For planning purposes, obviously the interconnect between the various devices is important. A physical representation of the various chiplets or the die involved, along with what the platform is that these devices will sit on. So there are tools for each of those disciplines, and they each have their own formats. The silicon team will use a set of place and route tools or a custom layout tool to design the die, and it will have, for the rest of the system, that appears somewhat like a black box. But that black box has to interface with a package or an interposer. And so the interposer design team needs to know what that interface looks like, both from a netlist perspective, what's connected to what, but also the physical bump layout. So that information can be shared in any number of formats. There's some industry standards such as LEF and DEF. There's GDS, which is widely used, and often just simple XY reports in Excel or CSV file formats are used. And then the other tools will need to consume them. So the challenge is, when things change, how does each tool get updated? Now, formats like LEF-DEF that can be passed back and forth between the planning tool for the interposer planning tool or the package planning tool and the silicon tool, those are possible, and they work well when all the pieces are available to both design teams. And we do have customers that are using the optimization aspects of our planning tools to move bumps around to make the package design simpler, and passing that proposed bump change back to the silicon team via DEF files. And then the IC team can accept them, and they become part of the solution. At the same time, you have input from a board team where, often the PCB design needs to understand or has influence on the package design, but you don't have quite the level of industry standard interchange formats between the board and the package or interposer teams like you do from the silicon world. The silicon data formats are far more standardized and common than the PCB formats, although we have found that ODB++ is an excellent interchange format for bringing in PCB data or package data into the planning environment for collaboration and optimization. So it is possible, and we have many customers working with that, and they're able to make trade-offs of both the package and the board and communicate those recommended or suggestions back to the other design team back in formats that are native to those tools, both Siemens and some of our competitive tools. Various implementation solutions, depending on the technology, it sort of dictates what sort of an implementation tool that the substrate team will use. And often it also dictates which implementation team will do it. For example, if a design requires a silicon interposer, often that will be done by a chip design team using an IC place and route type tool. If it's an organic package or a fan-out package, these type of designs are more commonly done with packaging solutions and using a different set of tools, package layout, whether it's from Siemens or from Cadence or some other providers. All of these solutions can all work together in a comprehensive planning environment. So the Siemens solution is not a full Siemens only flow. It works well with place and route tools from some of our competitors, as well as packaging tools from some of our competitors. And they work best with a full Siemens solution, of course, but it's not dictated to that. One of the other aspects of the 3D-IC design flow is the physical verification and the differeces between physical verification of the individual pieces and physical verification of the total solution. What this means is, I may be able to verify my interposer by itself or my package by itself, and the die, we may assume that the silicon team is, they've performed DRC and LVS at the die level, so they're known good. But how do you verify all of these pieces when you put them together are connected correctly? They line up correctly? When you meet with teams that are doing some sort of stack substrate design, interposer on package, et cetera, or multiple die on a package, there's almost always a horror story where some part of the layout was done and somebody interpreted one of the specifications as pins up or pins down instead of the correct orientation, and they ended up building and manufacturing a piece of it mirrored from the die or from the interposer. How do you prevent those types of things from happening, or those types of design errors from happening? And you need to do a comprehensive verification of what we call the entire assembly. And that is to take all of the pieces, the die, the interposer, the package, even the PCB if it's available, and put it all together in a single environment and verify that all of the pieces line up. How do you account for die scaling? How do you account for flipping and rotation and making sure that all of the die bumps or the interposer bumps and the package all line up, all the things land together? Now, these newer processes, almost everything involves some sort of die scaling. So you've got scale factors, and if the die is scaled at 0.9995 and there's a bump compensation factor on the package, how do you account for all of these things so that when you put everything together and manufacture it, it works? We have a comprehensive set of tools that are driven out of our planning tool to do what we call assembly verification. So this allows you to make sure that all the bumps are aligned. All the bumps have a corresponding bump on the mating, whether the die mating to the interposer mating to the package. There's nothing left out, and then there's nothing extra. That all the net names are correct across the tool, so that we didn't create shorts when they're connected together. Everything is nice and DRC clean, LVS clean independently, but when you put them together, you introduce connectivity shorts. We have a solution to account for that, which is probably the area that is most active for Siemens in the 2.5D and 3D IC design. People also refer to this as system LVS, and that is, kind of doing LVS of the whole entire system to make sure that the various design domains. The package design may call a set of nets clock CLK. The interposer team has the clock signals are similar names, but not exactly the same. And then the die calls them yet again something else. How do you validate the connection from the package bump, BGA bump, through the package to the interposer C4 to the die, that clock connection from the BGA to the die is correct through all the net name transitions, all the interconnect with the various layers of the package, the various layers of the interposer. And how do you do all that? The Siemens planning and verification platform allows you to do that. Those type of problems, finding them when you have a multi-substrate, multi-die system, finding those before you fabricate it is really, really important because it's very expensive when you don't. One of the areas that we are kind of seeing some emergence recently is in the area of logical equivalency checking. And this is mostly coming from silicon teams who have been using logical equivalence checking at the chip level for years now to verify that the netlist, the RTL implementation matches the synthesis and implementation of a physical layout. Similarly, there's questions, okay, if I've got a verification netlist of my entire system, and I've now got a package that's been, maybe it wasn't imported from the verification netlist, maybe it was hand created by somebody maintaining a spreadsheet. How do I know that netlist is correct? So I want to verify that the Excel file that the project lead put together and the netlist that goes into the package implementation tool is the same as what the verification team and design team, it's equivalent. So the ability to produce a Verilog netlist of a subset or all of the complex package assembly, the 2.5D or 3D assembly, is becoming important to answer that question. Are these two things the same? Yes, they are the same by teaching it equivalence points or defining equivalence points from the package physical netlist against the verification logical netlist. And then similarly, the desire to do actual functional simulation of the package design using the real RTL models that the verification team worked with to yet again verify that the system is, from a physical perspective, implemented correctly, the netlist is correct, and functions as expected.
Well, thanks, Mike. That was a lot of great information to take in. For listeners who are new to 3D IC design, but knowledgeable of traditional semiconductor package design, what areas should they focus on embracing first?
I think the easiest place to get started is with what we will refer to as the assembly verification. That is the ability to take the package netlist and the silicon die or multiple silicon die and verify that system is correct using the same solution we use for a multi-die, multi-substrate verification can be used for single die and single substrate. And even those type of verifications, while they're fairly straightforward, we still find customers finding it valuable to identify some mistakes, especially early in the design cycle. You don't have to have the complete package implemented in order to find value in this sort of verification, because simple things like the pins up, pins down type mistake I mentioned earlier, that can be found very early by doing an overlaps check between the silicon and the package, just to verify, yep, we've got the orientation correct, we're working this correct orientation as a silicon team, and we've got all the bumps in the right spot, and the silicon team hasn't changed any of the bump locations since we got their last snapshot. So those type of checks are quick to run, they're high value add, and they're easy to do early in the design cycle. So that's where we recommend get started. And by setting that up early, it makes it very easy to run those sort of checks every time there's an update from the silicon team. Or as the design matures, the implementation is done, adding LVS to that type of verification becomes very simple later in the design process, and it almost becomes push button. So that's where we recommend starting and then growing from there.
Thanks, Mike, for this highly informative discussion in this 5th podcast on 3D IC. And thank you, our listeners, for listening and subscribing to this podcast. Be sure to join us for future episodes as we continue to discuss 3D IC and other emerging integration technologies.